Okay, we are answering paper type purple in the year 2012 physics UTME questions. The first question is number 45 on nuclear physics. Now, the process of detecting a pin mistakenly swallowed by a child is X-ray what? Now, we have options. You say X-ray diagnosis, that's option A, diagnosis. Then we have therapy, right? We have crystallography, then we have mammography, okay? Now, looking at these questions, which of them answers? They said the process of detecting a pin mistakenly swallowed by a child is X-ray what? First and foremost, it cannot be X-ray therapy, okay? It is not X-ray therapy, so that is it. You know, the treatment is just to detect. All right. Now, we have to look at crystallography and mammography. Right. When we talk of crystallography, X-ray crystallography is a tool used for identifying the atomic and molecular structure of a crystal, right, in which the crystalline atoms cause a beam of incident X-rays. The incident X-rays to diffract into many specific directions. Okay, and materials like salt, metals, minerals, and semiconductors, they form crystals. Okay, so it's a means of you can call it X-ray imaging. Okay, so that is crystallography, to analyze the crystal structure of materials. Okay, now mammography also is just to detect application of soft X-ray to detect breast cancer, okay? Detecting breast cancer, right? So crystallography and mammography, right, they fall under X-ray diagnosis, okay? So X-ray diagnosis is for detection, right? Detection of atomic structures, molecular structures, materials, you know. So the answer is X-ray diagnosis. That's what encompasses all these. Sorry, C and D, whereas B is not among our options to be considered at all. So the correct answer is X-ray diagnosis. So we have diagnostic X-rays. Okay, we use diagnostic X-rays to study for X-ray imaging particularly. Okay, in medical lines, it is used to study the internal structures of human bodies, which has been prevented from, by the skin, right? So that answers the first question. Now the second question is number 46. Number 46. Which of the following particles cannot be deflected by both electric and magnetic fields? Cannot be deflected by both electric and magnetic field. We have gamma rays, right? We have alpha particles. We have wave particles, and then lastly we have beta particles. Okay, we have beta particles. Of all these, we know that beta particles, they are high speed electrons, so they are negatively charged. They carry negative charge, so they are deflected towards the positive plate, while alpha particles are nucleus of helium, and they are positively charged. Sorry, this one will be deflected towards the positive plate because it is negatively charged. Law of charges. Unlike charges attract, while like charges repel. So beta particles are negatively charged, therefore they will be attracted towards the positive plate. Now, alpha particles, they are positively charged, so they will be deflected towards the negative plate. Alright, gamma rays are neutral, they carry no charge, just like any other electromagnetic waves. Any other electromagnetic waves, they don't carry charge, they are neutral when it comes to charge. Therefore, they are not deflected by both magnetic and what? Electromagnetic. By both magnetic and electric field. Okay, so the answer is gamma rays, option A. Alright, we cannot say wave particles because we have different wave particles. Good. We have electromagnetic waves and we have mechanical waves. So, alright, now the last question is a calculation question. A piece of radioactive material contains 1,000 atoms. That's number 47. If its half-life is 20 seconds, the time taken for 125 atoms to remain is what? The time taken for 125 atoms to remain is what? Now we have initial particle to be 1,000 atoms, right? And then we have remaining particles to be 125 atoms. So, and the half-life here is 20 seconds. So the question is, what the time taken for the particle to decay down to what? From 1,000 to 125 atoms. Very simple. You meant to draw stuff like this. Okay, draw stuff this way. This way. Alright. Now, we have partitioned it this way. Okay. Now, we look at time and the particle remaining. When time was 0, the particle was 1,000. Alright. Immediately 20 seconds elapsed, we have half of it decayed. So we have 500 atoms left. You understand that? That is half-life. Is the time taken for exactly half of a particle to what? To decay. So half of 1,000 decays, so we have 500. After another 20 seconds, this 500 decay to half, so it becomes 250. After another 20 seconds, this 250 decays to what? 125. So it takes how many seconds for 1,000 to become 125? That is 20, 20, 20. So the answer is what? 60 seconds. So it takes 60 seconds for 1,000 atoms of a radioactive particle to decay down to what? 125 atoms. Okay? Right. Alternatively, we can say particle remaining is equal to initial particle times half raised to power time taken to decay to the remaining particle, then over what? Half-life. So particle remaining here is 125, initial particle 1,000 times half raised to power time, which you don't know, half-life, which is what? 20. Alright, so we have what? Divide 1,000, that means by 125 over 1,000 will be equal to 2 raised to power minus t over 20, right? 125 over 1,000 is 1 over 8, right? That is 2 raised to power minus t over 20. Giving us 2 raised to power minus 3 is equal to 2 raised to power what? Minus t over 20. 2 cancel 2, minus cancel minus. So what do we have? We have 3 is equal to t over 20. Cross multiply, we have t equals to what? 60. So the time taken is what? 60 seconds for 1,000 atoms to become 125 atoms. Remember from this formula, this is the particle remaining after decay has taken place, the initial particle, time taken for the initial particle to become this remaining particle, and this is what? The half-life. Right, thank you very much. You can always visit my blog for any videos that you like. I wish you all the best. Thank you.